Hello, video 2 on waves, boundaries, superposition and interference. Superposition, we can sometimes call it superposition or superposition, your choice. Okay, let's look at some waves, or more precisely some pulses. And the difference between a wave and a pulse is a bit arbitrary, but basically it's a single wave, and so this here would represent a pulse. Now pulses can be any shape or size. In this case it's a triangular one, but it could be curved, it could be a square. That's just there's no definition of what shape it has to be, and you'll see examples of all sorts of different shapes. So here we have a spring. This is representing a spring, and we have a fixed boundary. And so what we're asking here, or what we're going to learn, is what happens to this pulse when it comes to this boundary. What happens to the energy that's involved in it. So what do you think? It's going to get reflected, so it's going to bounce off it, but what's it going to look like? Well, it actually looks like this. So you can see now it's on the opposite side, and it's instead up here it's traveling left to right, here it's traveling right to left, and what we would say is that this pulse has been inverted. Another way of saying it, it's out of phase, or it's 180 degrees out of phase. Remember when we saw that graph displaying a wave function, and we had 360 degrees described the full pulse, so 180 is half that. And so we're saying it's out of phase. Now this is for a fixed boundary. Okay, so that's like if we've plugged it into a wall or something. Here we have a free end, so this end is able to move, but energy will still be reflected back. And so what's going to happen? What do you think it might look like? In this case, the pulse here, we have a trough first, and then a crest. So this pulse is moving from left to right, and when it gets reflected, remember here we had a trough first and then a crest, and what we see coming towards us again is a trough and a crest. So although it looks reversed, it is reflected, but there's no phase change. Do we understand that? Hopefully. Okay, what happens here? Here we've joined two springs, a light spring and a heavy spring. Of course it's heavy, it sort of acts like a fixed end, but it's not like a wall or something. Some energy will go into this spring, and so here we have our pulse moving from left to right, and some of the energy will go into the heavy spring, and some of it will be reflected, and it will be inverted. Okay, so that's what's happening there. So the sum of these two energies would equal that energy, assuming nothing's lost to heat or noise or anything else. Now what's happening here? Anything? Right. Here we're going from a heavy spring to a light spring. Now this acts more like a free end. Okay, and so here we only have a small amount of pulse removed. Now notice that the wave length here is considerably longer than it was here, so we've actually had some transition happening, but this is reflected, and we're saying going from a heavy spring to a lighter spring are reflected in phase and transmitted in phase. Now there's an animation here. Alright, now let's see if I can bring this up. I need this, and then this, and then this. Okay, let's have a look at this. Here's a little animation, and I'll put this on the OneNote or make it available somehow, and so I'll just quickly demonstrate what it can do, and then you guys can have a play on it when you get an opportunity. So here I've set it as a pulse, and if I send a pulse, there goes the pulse. It's coming to a fixed end. I've got full tension, I've got no dampering. If I enter dampering, the energy dissipates. Okay, and I've defined the width and the amplitude, so I can send a number of pulses, and those pulses will interfere with each other. We're going a little bit ahead of ourselves, and we'll learn how to do that shortly. And if I put it at a loose end, we just go send a pulse. What's going to happen this time? It goes like that. Yeah, and that's pretty straightforward. But you can oscillate it and send waveforms. We'll be doing that again when we do standing waves. Ooh, quick, let's reset that. That's gone crazy. And what if there's no end? There we go. Pulse goes out the door and is lost forever. So I'll put that on our OneNote, and you should be able to have a look at it. Now let's see if I can get back to this. Yes. Okay. So let's look at now superposition and interference. So we just hinted at some of that. When two sets of waves, they can pass through the same point without affecting each other, and it happens all the time. If you're in a crowded room and a lot of people are talking, all those sounds are going through each other, but they're not making a jumble. You can still distinguish individual people talking, and so that's exactly what's happening here. We're going to simplify it down a little bit, just into a couple of pulses. However, they have a combined effect, and if we want to look at their combined effect, we use vectors to look at them, and this is the principle of supposition or superposition. So here we have two pulses. One's travelling to the left and it's a triangle. One's travelling to the right and it's a triangle. One's travelling to the left and it's a semi-hemisphere. Okay, and when they pass through each other, this blue line represents the pulses and the red line represents what the spring would actually doing. And what you're getting is a combination of those. So here, this little lump here is because there's positive energy there and positive energy from this pulse, and it all adds up. Not the clearest diagram, but we'll get some more. And if we move along a little bit further, we get this. Now this is only for an instant as they pass through each other. So it's a very local disturbance, and then they pass on their merry way undisturbed. Okay, and it's just recapping all that. That makes sense, hopefully. This one probably details it a little bit better and what we're trying to talk about in the vectors. These are the vectors of movement of the particles. Here we have a large pulse and a small pulse, rectangular. When they're coinciding like this, the resultant is the addition of the two vectors. Okay, so we've got this vector plus this vector, and this is the resulting pulse. Okay, and then they pass through each other and you just get the regular amount of movement. So you should now be able to have a go at questions 6 and 7 in your workbook. Joy. Now we're going to introduce some terms called destructive and constructive interference. Destructive interference is when waves cancel each other out. Constructive is when they add to each other. And so here we have destructive interference of two pulses. We've got a crest moving to the right and a trough moving to the left. There'll be an instant when they coincide, and it's this instant here where there'll be nothing, and then they pass through each other, and we'll show you a diagram that helps you understand this a bit more. And they just pass through without anything happening. Here we have, and that's called destructive interference. Effectively there's an instant when there's no wave, even though the energy is still there, but it's only for an instant. Here we have constructive interference, so we have two crests, and when they coincide with each other for this instant, because we add up these vectors, moving upwards vectors, we end up with what's called a supercrest. And that supercrest exists for an instant, and then the pulse is passed on. Now if these were troughs, we would end up with a supertrough. Okay. When pulses collide, now we got a video of this. Let's see if I can bring this up. Here we go. Alright, this looks good, all looks good. Let's play. So what this is showing is we've got this sort of rectangular pulse, and we've got this trough, and when they come together the pulses add and subtract. So the particles themselves, here particles have to move up 2 squares, here particles have to move down 2 squares in the medium. So when they coincide, let's just bring it along, we get the addition of these two, and this is the resultant. So if we think here, this particle, the particle here has to experience 2 squares down because of this pulse, but 2 squares up because of this pulse, and so the net result is nothing. Whereas this particle here has half a square of down, but it has 1.5 squares of up, therefore it moves 1 square up, and that's why you get this sort of funny shape here. And if we move it through a couple of times, we can see that the pulses then pass through each other. Okay, we're waiting. Here it comes. Let's go again. Did I pause it? I must have. Oh, it stopped. It's crashed. Oh no! Come on. Okay, clearly it doesn't want to show again. Let's get rid of that. But hopefully that made sense for you. Okay, let's just do it again. Now, that doesn't have to be single pulses, it can be multiple pulses or a wave. And so here we have 2 waves interfering with each other. Now here we've got a trough and a trough coinciding, and a crest coinciding, and a trough and a trough. So when these waves coincide in exactly this position, you get super troughs and super crests. Note the amplitude is twice the height, but the wavelength remains the same. Here we moved, the waves are slightly out of sync. They're out of sync, let's say 90 degrees, or a quarter of a wavelength. And so, is it a quarter of a wavelength? Yeah, I think it is. No, it's half a wavelength. And so we're getting a trough, so it's 180 degrees. Here we have a trough coinciding with a crest, and a trough coinciding with a crest, and so the net result for this instant is nothing. Okay, but remember these pulses are moving, and so this pattern is not static. Just showing it again, this is constructive. These are when the waves are in phase, they reinforce each other. Constructive interference. This is when the phase difference is half a cycle. There we go, we've got it in words. I worked it out right. 180 degrees, and they cancel each other, so you get 0 amplitude. This is destructive interference. So in the next wave, we're going to look at what are called, in the next video, not the next wave, in the next video we're going to look at standing waves. Alright, see ya.